Hi everyone, we're going to go into the rest of Chapter B today. So now this next topic here in Chapter 4B combines solving limiting reactant style problems, but now working with solutions. So let's go into this practice problem. We've seen limiting reactant style problems before, so let's continue on here. And we're going to suppose we have this mass of sodium iodide. I would write out just for practice, and we might need this later. So sodium iodide, right? So Na and I minus, dissolved in 50 mils of a 51.00. And then with this one, I would see this lowercase m and instantly think milli, and then capital M molar. So with this, I could picture writing out right away that this is millimoles of solute per liter of solution. So 51.0 millimoles, right? Because millimolar, molarity is still moles of solute per liter of solution. So now millimolar here. Now, interestingly, the solute here is silver nitrate. So I'd probably also get practice writing out this. So silver Ag plus, nitrate NO3 minus, right? So referring to your note card or that table, or you have this memorized now. So then silver nitrate is AgNO3. We don't need any different subscripts here because this is +1 and this is -1. So this is technically our solute based on this description here, so aqueous solution of silver nitrate. Then calculate the final molarity of the iodide anion only in solution. So now we're using limiting reactants, but we're also looking at solutions of ions or solid or semi-solid precipitates. So we have ions in aqueous solution and maybe some insoluble precipitate as well. So let's go into this practice problem. So now with these style problems, we've made this sort of table before together. And what we want to do is take all the species that are present in our solution. So we're told we have sodium iodide, so Na plus and I minus. We also have aqueous silver nitrate, so Ag plus and NO3 minus. Then, as mentioned, we're going to calculate this molarity of just the iodide anion here. So just this iodide anion. And as mentioned too, in solutions, we can have ions that are in aqueous solutions, so they're soluble, or maybe some combination of the cation and anions are insoluble. So remember, if they're insoluble, then they form this solid precipitate. So now let's figure out if any of these combinations of cations and anions are insoluble, meaning they'd form these precipitates. So now for our selection of cations, we definitely had Ag plus. So that Ag plus can either be with our anion of nitrate. Our other anion present is I minus. Then the other combinations, we also had sodium. So Na plus and Na plus. Then again, that sodium could be combined with an anion of nitrate, so NO3 minus or I minus. So now we'd look at our solubility rules and figure out, are these combinations soluble or insoluble? And so one right away for sodium, this is always soluble because it's one of the group 1 metals. So group 1 metals, so sodium with any of these anions is going to be soluble. Then if you look at your solubility rules for nitrate, you'll also notice that this combination is soluble. So a nitrate anion with silver, that combination is soluble. If you have any questions about how to read those solubility rules from the table, please let me know and we can talk through how we figure out this combination is soluble. Then the next combination possibility is silver and I minus. When you go to the solubility rules, you'll see that this combination is insoluble. So it's insoluble, meaning this combination will form this solid or semi-solid precipitate. So with this combination, we could write out a reaction that's happening. So we could have Ag plus ions in solution and I minus ions in solution, where the I minus came from sodium iodide. The Ag plus originally came from the silver nitrate. So you have those two ions, they will come together to form this insoluble precipitate. And the formula for that is AgI, because this is +1, this is -1. So there are also subscripts of 1 here. So this forms a semi-solid or solid precipitate. So again, with this style problem, you want to list your cations and anions and go to your solubility rules and see which combination leads to an insoluble precipitate and which combinations of ions are soluble. So I wrote out our reaction again here, and in dealing with the formation of this precipitate, it's going to be impacted by how much silver is present in the solution and how much I minus is present in solution. So how much silver cation and I minus anion. And we know the silver plus came from, again, the silver plus is going to come from the aqueous solution of silver nitrate, and then the I minus comes from this sodium iodide. So as we're picturing the Ag plus and I minus coming together from two different sources to form this solid precipitate, this is where it turns into this limiting reactant style problem. Because is the silver going to run out first, or is the I minus going to run out first? And then that'll tell us how much AgI solid there is that can possibly form. And we need to know, is the silver going to run out first, or is the I minus going to run out first? Because our problem is asking for the concentration, the final molarity of iodide anion in the solution. So we need to figure out how much is going to be used up of the NaI to go into forming AgI. Then whatever is left will be our I minus left over in solution. So let's use what we know about the sodium iodide and the silver nitrate to tell us how much Ag plus and I minus there could be in solution, and then see how much will then form that solid precipitate. So let's just first find out how much is in solution. So we know there are 0.650 grams of sodium iodide in solution, but again, we're just interested in how much I minus comes from that sodium iodide. So to figure out how much I minus from this whole ionic compound, we can think about this NaI solid then gets put into water and forms these Na plus ions and I minus ions. Now this is already balanced because, again, these subscripts are 1 and 1, so we don't need to change these molar coefficients here. So this is NaI solid goes on to produce 1 mole of Na plus and 1 mole of I minus anions and cations. So this is all 1 to 1 to 1 mole ratio. So here we have grams of NaI, so 0.650 grams of NaI. We know we need to go into moles, right? But right now we're working in NaI. So we need to use the molar mass of sodium iodide to then get moles of sodium iodide. Then we can use this balanced chemical equation to connect moles of sodium iodide to moles of I minus. So now for the molar mass of sodium iodide, if we go to the periodic table, look up the mass of sodium and iodine, we add those together. This comes out to 149.89424 grams per mole. To orient this correctly, we need to put grams in the denominator, so then we'll be left with moles in the numerator. So here we'll have 149.89424 grams per mole. And to be really careful in labeling all this, we can go ahead and add in, this is specifically grams of NaI per mole of NaI. Doing this division here, we get 0.0043364 moles, but specifically still of sodium iodine, or sorry, sodium iodide, right? The IDE ending is important. So sodium iodide is this many moles. Now we actually want the moles of just iodine, right, or the iodide anions. So now we can set this up to say 0.004334 moles of NaI. Then using this balanced chemical reaction for the dissociation of sodium ions and I- ions, we can then make this connection. So this is a 1:1:1 mole ratio. So it's a little bit more straightforward of a connection, but it's important to know how to work with this when it's not 1:1 molar coefficients. So here we're going to have for every 1 mole of NaI, right? 1 mole of NaI, there's 1 mole of I-. So here moles of NaI and moles of NaI cancel out, and this is the same mole amount of I-, but again, it's important to do this mole to mole ratio to then prove that. So really we are going to get this same number because it's that 1:1 mole ratio, but here it's 0.004334. It should be a 3. And this is now moles of just I-. Okay, so we got that step, and it's this 1:1 mole ratio, but this is actually really important too. Even if it is a 1:1 molar ratio, it's really important to know how to make this connection here to connect moles of NaI to moles of I-. So now with these dissolutions of a solid, just to show you some other examples here. So if we had K3PO4 or potassium phosphate, as this dissociates into ions, this 3 is the subscript here. So that 3 has to be the molar coefficient for these potassium ions. Then there's 1 mole of phosphate ions here because PO4 3-. This doesn't need a molar coefficient because this subscript is just an implied 1 here. So be sure you're comfortable doing these dissociation and balancing these reactions. So here K3PO4, there's 3 potassium ions for every 1 phosphate anion. So +1 charge for potassium, 3- charge for phosphate. So now at this point we have the moles of I-, and now we can work with getting the moles of Ag+. So let's practice writing out this dissociation. So silver nitrate, we're told it's already an aqueous solution. This dissociates into Ag+, aqueous, and nitrate minus, also aqueous. So Ag+ and NO3-. This is already balanced because this subscript is 1. This subscript around this whole polyatomic anion is 1. So here we have a 1:1:1 mole ratio between silver nitrate, silver, and nitrate ions. Now we weren't given a mass this time, but we were given this concentration in millimoles per liter. So this is 51.0 millimoles of silver nitrate per liter of solution of silver nitrate. So now we can use this to end up getting moles of silver. So here we have 51.0 millimoles of silver nitrate, right? That's our solute per liter of solution. Now, the other piece of information we need in addition to this molarity here is going to be this volume here. So we're told the volume of this concentrated solution, this 51.0 millimolar concentrated solution, we have 50 milliliters of it. So now we can use that here. So then we have 50 mils of it. Let's put 50 mils in here. We ultimately want moles of silver nitrate to then connect that to moles of silver. So we are going to want to cancel out a volume term. So 50.0 milliliters can be here in the numerator. But importantly, we're not yet done with the volume term because we have to cancel out or get milliliters into liters. So now for every 1,000 milliliters per 1 liter. So at this point, we're canceling out mils and mils, liters and liters. Right now, we just have this in terms of millimoles of silver nitrate. So let's keep going now. And so for every 1,000 millimoles, there's 1 mole. So at this point, we could also then cancel out millimoles and millimoles. And if we do this whole multiplication and division, we're going to have moles of silver nitrate. So that equals to 0.0025500 moles of silver nitrate. So I'm going to keep this label here because we have not yet connected this officially to just the moles of silver. So right now this is still moles of silver nitrate. Now to connect this to just our moles of silver, we have 0.25500 moles of silver nitrate. And we need to formally connect this to the moles of silver using these mole to mole ratios. Again, this is a more straightforward one because the ratios are 1 to 1, but always practice doing this even if the ratios are 1 to 1, because at some point they're not going to be 1 to 1. It could be, 3 moles of silver nitrate to 2 moles of something else. Okay, so let's just look out for those examples where they're not just a 1 to 1 mole ratio, and you would know that because then these subscripts are not 1 to 1, because these charges are not the same charge, right? So this is +1 and -1. So then these subscripts are 1 and 1. So that makes this whole mole to mole ratio here be 1 to 1. So what we're getting at is we're going to put 1 mole of silver nitrate, right? Because that's the molar coefficient here for every 1 moles of silver ions. Okay, so we are just taking this value and multiplying it by 1, but again, watch out for the non-1 to 1 mole ratios here. So that means we can also say we have this many moles now also of our silver ions, right? Because if we do this cancellation, then we have just moles of silver plus left. So we're taking this value multiplying by 1. So now we have moles of I minus. We also just calculated the number of moles of Ag plus. Now in solving these problems, I did also bring up using a rice table at one point. So we can also practice solving this using that rice table, where R is for reaction, I is for initial amount of moles, C for the change or the loss in moles, and E at the end also in moles. So let's practice doing this rice table again. So for our reaction here, we do have Ag plus and I minus, both aqueous, that go on to form a precipitate of silver iodide. So here's solid. Now for this table, we do have the initial amount of moles of each of these ions already, right? So for I minus, it's 0.0043364. So 0.0043364 in moles, importantly. So for the rice table, in moles. For most stoichiometry problems, you're going to want to work in moles at some point. So probably all stoichiometry problems at least connect back to moles at some point. Then for the silver, we just calculated that. So that is 0.0025500. So now we can put that in 0.0025500. Then for the initial amount of our product, do you remember what we put in here? So for the initial amount of a product, there is no product yet because we're just starting out. Okay, then for the limiting reactant style problems, if you remember doing this, we're going to say that this changes to be minus x, and we just have a 1 here because this molar coefficient here is 1. So this is minus 1x. If this were not a 1, you need to put in 3x or 4x or 2x. Then for the I minus, this also is a molar coefficient of 1. And for this limiting reactant style problem, we want to figure out what's the smallest variable. So I'm going to assign this just arbitrarily y. And this is a minus sign because we're going to lose concentration of our initial reactants over time. So as the reaction is proceeding to form this product, we're going to lose some amount of silver plus, we're going to lose some amount of I minus. So now let's go ahead and figure out what's the smaller variable, because the smaller variable then is our limiting reactant. So for silver plus and I minus, we're going to arbitrarily say that this gets completely used up and this gets completely used up. So let's solve for this variable for silver first. So to do that, we take 0.0025500. So this value here for the initial moles of silver plus minus 1x is equal to 0. Actually, I wanted to rewrite it like this so I could better visualize it. But if we add x to both sides, then x is equal to 0.0025500. So that's our variable for silver. Then we do the same thing for iodide. So we have 0.0043364 minus 1y is also equal to 0. Remember, we want to figure out what's the smaller variable to tell us which one is a limiting reactant. So then we're adding y to both sides. So y is equal to 0.0043364. So now based on these values, we can successfully identify that silver ions are our limiting reactant. So this variable here is smaller than this variable. So here our limiting reactant is silver. What does that mean then? If silver is our limiting reactant, it means that all of these moles of silver are going to go in to form silver iodide. And at the same time, some of the I minus is going to be used up as well to go into form silver iodide. But because silver is our limiting reactant, it gets used up first. Then we'll have some I minus that remains. Okay, so we use the Rice table to find out what is our limiting reactant. There's also the guess and check method. So for more of a review on limiting reactants, definitely go back to chapter 3 or let me know if you have any questions. So we did figure out the smaller variable using our Rice method is for silver. So silver is our limiting reactant. It's going to run out first. So silver ions are our limiting reactant. They're going to run out first. And so for silver, we have this many moles. For iodide, this many moles. So to figure out how much I minus is left over, that is our answer that we want in the end. So all of the silver is going to get used up. Then how much I minus gets used up to form AgI, or silver iodide precipitate? Well, here we have another 1-to-1 mole ratio. So this is an implied 1 here and 1 here. So now technically we could just do the subtraction, but I want to show you formally how we get this value here as well. So how much I minus is needed to fully react with the Ag plus. So here there's this many moles of Ag plus. For every 1 mole of Ag plus, there is 1 mole of I minus. So again, this is a simpler one because these are 1-to-1 mole ratios, but I'm kind of showing you how you should approach this either way, just in case these end up being non-1-to-1 mole ratios. Moles of Ag plus cancel out, so that means how much I minus is needed to fully react with the silver plus. That is 0.002550 moles of I minus. So this many moles of I minus are needed to fully react with our starting amount of silver. So how much is left over then is our initial amount of I minus, so 0.0043364 moles of I minus. This is how much we started with, minus how much we're going to need to use up to match how much silver there is. So now this is 0.0025500 moles of I minus. This is how much is needed to react with Ag plus to completion. right? So then we get this answer here that we have this many moles of I minus left over. So that's 0.001784 moles of I minus remain after all of this amount has reacted with silver, and we started with this much. So with this many moles of I minus remaining, then let's go on to further answer our question. We have this many moles of I minus. We're told in the problem we want the concentration of I minus or iodide anions left over in solution after this precipitate forms of silver iodide. Then this is still all in the same volume solution. This has all been happening in 50 mils of solution. So now to solve for our concentration here, because we want the final molarity, and we have the moles of I minus, then we can go ahead and plug in here. So 50.0 mils, but very importantly, we want molarity. For all molarities, we have to report them in moles per liter, not millimoles, not milliliters, not decaliters, not micromoles, always moles per liter. So now this is in moles per milliliter, so we're not done yet. We do need to convert 1,000 mils in 1 liter. Then mils and mils will cancel out, leaving just liters and moles, which is what we want. So now doing this times 1,000 divided by 50 gets us 0.03573 moles of I minus per liter of solution. Technically, this is just 50 point mils, so I shouldn't add that extra zero here. So this is just 50 point mils. Then for our final answer, we want this in 2 sig figs, because this is just 2 sig figs here, right? 2 sig figs, 1, 2. Then to get this into 2 sig figs, 0.03, this gets rounded up to 6, so 0.036 moles. Divided by liters, then moles per liter is in units of molarity. So that leaves our final answer now of 0.036 molarity. There are some other practice problems in the main slide deck. And let me know if you have any questions, as always, about limiting reactants, solubility, other matters that we've gone through in chapter 3 and 4 now. The next topic we're going to get into in chapter 4b is determining the molar mass of an acid by titration. So we talked more about acids and bases. We're going to talk more about titrations now, how we can determine the molar mass of an acid by titration. So let's talk more about titration, then we'll do a practice problem. So in a titration, a solution of an accurately known concentration is added gradually to another solution of unknown concentration until the chemical reaction between the two solutions is complete. So being in the lab, this is a burette. So this is a burette. Some of you have used a burette now in lab, but this is a burette. This is where our known concentration is going to be. So in our burette is where our known concentration of a base or an acid, or even a different chemical here that can be done for a redox titration. We'll talk about that just a little bit at the end. So in our burette is our known. This is added gradually to another solution of an unknown concentration here in one of our Erlenmeyer flasks. If we had a base, let's say we're adding a base to an acidic solution here as our unknown. As we're adding a base to this acid, what we term now is our equivalence point, where our equivalence point is the point at which the reaction is complete. So for an acid-base titration, this can be when we're at a neutralization point. For redox titrations, the equivalence point is different. It's when all the electrons have been transferred that can be transferred. But for a general titration, this term equivalence point, the point at which the reaction is complete. Then our indicator is a substance that changes the color at or near the equivalence point. It changes color at or near the equivalence point. This means that we add some indicator here to our unknown. And we need to add the right indicator because as this reaction, in this case a neutralization reaction, is reaching the equivalence point, this indicator will actually change colors as the solution goes from acidic to neutral, then to basic. So the indicator here is the substance that changes color at or near the equivalence point. And again, the equivalence point is the point at which the reaction is complete. So often a sample of acid can be titrated with a base to find the concentration of the acid. So in here, this would be a known concentration of the base and it's added to an acid. So a known volume of the sample is placed into a flask here, along with an indicator. A common indicator for acid-base titrations is phenolphthalein. It's used visually to indicate the pH of the solution. Phenolphthalein can be a nice pink color. It just depends on the different indicators, but there can be some really pretty colors of indicators like orange, blue, things like that. So phenolphthalein is just one example of an indicator. Then samples with this indicator are colorless in an acidic environment, but they turn pink in the presence of a base. So as the acid starts to neutralize with this base, it'll turn from clear to then a pink color. So the pink color helps us visualize then that this is turning into a neutral and then eventually a slightly basic solution. And this flask is placed under a burette filled with the known concentration of base. So this concentration here in our burette would have to be a known concentration of base. We're slowly titrating that into our unknown concentration of acid, but based on how much base is needed to then neutralize this acid, we can then determine actually the concentration of this acid. So we can determine the acid concentration here in this unknown that's in our Erlenmeyer flask with the help of an indicator. So for these steps, we're going to slowly add the base to the unknown acid until the indicator changes color. Once the exact amount of base has been added to the acid such that all the acid has been neutralized, the end point of the titration has been reached. So the end point here, you'll see it turn pink when our acid goes into being neutralized and then slightly basic. So here it was clear, then we're adding more and more and more base, and then it turns pink here as it becomes neutral and then eventually basic. The end point is not when we get a basic solution. The end point here is when we neutralize the solution. So we're going to neutralize the solution, the acidic solution, by adding base, and the phenolphthalein indicator will change color to a faint pink at our neutralization point. Because keep in mind this definition of an endpoint here, where the equivalence point is the point at which the reaction is complete, but then our endpoint, the endpoint is still the point at which the reaction is complete, but now the endpoint is considered with a color change. Okay, so just a subtle difference here between our equivalence point and our endpoint. At the endpoint, we're going to see the color change. For an equivalence point, it's when the reaction is complete. These don't always perfectly match up. Generally, they do. So at our endpoint, the reaction is complete and we see that color change. So then by measuring the volume of the base that was delivered and the molarity of the base, the moles of the base delivered can be calculated. Using a balanced chemical reaction of our acid and base, the moles of acid that were present in this unknown can then be calculated. Then, because we know this total volume initially, we can find our now known moles of acid divided by the volume of our acid. So these were unknown, but then we used titration to determine these moles of acid, and we know this volume. The key point, coming back as always, we're going to be working in moles. That's one key point. We also then, to connect moles of base to our moles of acid, how do we connect moles of one thing to moles of another? Well, we have to know our balanced acid-base chemical reaction, and then we can connect the moles of base to our moles of acid. So we're about to do a practice problem now, and we'll do an example of this. So for example, let's say we have, if you recognize this name, this is sulfuric acid. This is a strong diprotic acid, right? There's 2 protons that can dissociate from this acid. Then sodium hydroxide, this is a strong base because it contains OH. So OH plus a group 1 or group 2 metal. So here's a group 1 metal with OH, so this is a strong base. This is hydroxide ions. Right, so OH minus is hydroxide. So we covered acids and bases previously, so for more of a review on acids and bases, go back and check out some past material in chapter 4. What we also covered, which is really important to writing out these products here, is this has to form a salt and water, right? So we take a strong acid with a strong base. We looked at previously that these 2 come together to form water and a salt. We can show the different ions that will dissociate, so Na plus and OH minus. H2 and SO4, this breaks down into 2H plus and sulfate, so SO4 2 minus. So we know with the H plus and the OH minus, those go on to form water. But for our salt, we have Na plus and SO4 2 minus. So Na plus and SO4 2 minus form our salt. Using the cross method, this is plus 1, this is 2 minus. This becomes Na2, right? This has to be balanced, and SO4 with just that subscript. So Na2SO4 is our salt. Then if we had these written out, but we didn't have this balanced yet, we could see that there are 2 sodiums. We should put a 2 right here. Then for oxygen, there are 2 and 4, that's 6. On this side for oxygen, we have 4 and 5. So then we could try to adjust this coefficient here. So if we have 6 oxygen and only 5 oxygen, this has 4. We're not going to change the subscript here. So we have 1 oxygen to deal with, which is here. So how do we make this oxygen be 2? We add this molar coefficient here. So now we have 6 total oxygens here, and then 6 total oxygens on this side. Hydrogen, we have 4, and now hydrogen, we have 2, and then 2 here. So now this is our balanced version of this strong acid with a strong base reaction. This is so important because now this molar coefficients, these molar coefficients in this balanced reaction essentially tell us that for every 1 mole of strong acid, there's 2 moles of strong base. So being able to take a strong acid with a strong base, note they form a salt and water, then balancing the chemical reaction, all of these topics coming back into importance here is crucial. So all these topics are definitely building on themselves now. So balancing reactions, taking strong acid and strong base, and even writing out these ionic formulas from 2 different ions. So Na plus and SO4 2 minus form this ionic compound of Na2SO4. So if you have any questions about any of these topics, definitely let me know. As I mentioned also, we're going to briefly get into redox reactions, or redox titrations even. So redox reactions we've worked on a bit now. So combining this idea of redox and titrations, we can actually form a redox titration as well, using different ions that we know react together in a redox style reaction where we have oxidation along with reduction. So I'll talk about redox reactions a bit here at the end of chapter 4b. Let's try this practice problem now. So we know that a chemist weighs out 0.122 grams of an unknown diprotic acid. This means that 2H plus can dissociate from that acid. So we know that there's definitely 2 protons in the chemical formula. Into a 50 ml volumetric flask and dilutes to the mark with distilled water. The chemist then titrates the solution with this molar concentration of sodium hydroxide. When the titration reaches the equivalence point, she then finds that she's added this many mils of sodium hydroxide. I like to visualize what's happening. So technically this is our base with sodium hydroxide. We are told that the base is titrated into the acid, the unknown acid. So here's our base, sodium hydroxide. We also know this is a 0.700 molar solution of sodium hydroxide. We also know that it took 26 mils to reach an equivalence point for our acid. So now in a Erlenmeyer flask, then this is our unknown acid. We do know that it's diprotic, so it's going to have H2 in the chemical formula. What else do we know? We have 0.122 grams of the unknown acid, and it's also in a 250 ml volumetric flask. So we have 250 mils of the acid where we originally dissolved 0.122 grams into a flask to make this concentrated acid. In the end, we're going to calculate the molar mass of the unknown acid that was used to make this acidic diprotic acid solution. So we talked about titrations a little bit. So chemists often use titration to accurately measure the amount of acid or base in an aqueous solution. So for example, in this case, the analytical chemist can measure the number of moles of acid in the original solution by measuring the amount of sodium hydroxide solution it took to neutralize this unknown acid. Right, so we know it took this many mils of this concentrated solution of sodium hydroxide. So sometimes measuring the amount of acid or base is all you want from the titration. Sometimes you need this information to solve for another type of problem. So for example, in this case, once the analytical chemist has measured the moles of acid in the original solution, she can then combine this with her measurement of the mass of the acid here. So this much mass of the original amount of acid to then find the acid's molar mass. So different styles of titration problems. Here we're going to find the acid's molar mass. So as mentioned with these titration style problems, it's going to be a combination of concepts here. So converting moles, mass, volume, and molarity, writing out balanced reactions from acids and bases. So writing out balanced reactions from acids and bases. For a strong acid with a strong base, this always forms a salt and water. So lots of different concepts here going into these titration style problems. So let's practice writing out a balanced chemical reaction. All we know from the problem is we have a diprotic unknown acid and we have sodium hydroxide, a strong base. Let's try to piece these together. And one thing we can do with this diprotic acid is say that this anion portion of the diprotic acid is just some arbitrary A. For example, if we have a diprotic acid like H2SO4, this portion here is our A because this is our anion. So H2 is the diprotic acid portion, SO4 is our anion, so SO4 2-. For our example, we don't know this portion, this anion portion, and we don't really need to know that portion, so we can just label it as this arbitrary A. So H2A, so some anion here. So this H2A, this unknown acid, reacts with sodium hydroxide, goes on to form a salt and water. So here we're going to form salt and water. The salt is going to come from Na+ and our anion. For this to be a neutral acid, as far as the charges go, then for H2A, this dissociates into 2+ because for every one hydrogen, it's plus. So really H2A would be one H+, another H+, because it's diprotic. For all of this to be a neutral molecule or neutral compound, then technically we're going to have a 2 minus. This anion portion isn't really crucial to getting the right answer here, but let's go ahead and continue setting up this balanced equation. So Na plus and A2 minus are going to form our salt. So then the formula for our salt then, using that cross method, is technically Na2 and A1, right? So this cross method here took plus down here, 2 minus right here. So remember, these components are going to have the opposite charges. So cation makes this anion have a subscript of 1. 2 minus for the anion makes this subscript for the cation be 2. So now we could write this in as Na2A. That's our salt. Let's check if all of this is balanced. So here we have Na2, here we have Na1. So we need a 2 right here. But then for oxygen, let's see, we have 1, and here we have 2. So we could balance this oxygen by adding a 2 here. But how does that impact the hydrogen? Let's see. We have 4, then 2 and 2. Now this is a balanced reaction with a general diprotic acid. This is the general form of a diprotic acid reacting with a strong base to then form water and a salt, again with this general unknown anion. To start writing out the net ionic equation then, we know H plus is going to dissociate. There are 2 of them. Then there's A with a charge of 2 minus. I'm leaving out these physical states of matter at this point, just to make it cleaner, but I will need to add those back in. So H2, there's 2 of them, A2 minus. For sodium, there are also 2 of them, O minus, 2 of them, goes on to form water. Water does not break apart into ions, generally speaking, so water is stable. Then there are 2 Na plus and A2 minus. So now to start canceling out ions that show up on both sides in the same form for the reaction, we can cancel out A2 minus, Na plus, leaving H plus and 2 OH minus, going on to form water. So that's what we would expect from a strong acid, strong base net ionic equation, where ultimately we have H plus cations and OH minus anions go on to form water. Now we went on to write out that whole net ionic equation, but I want to bring you back up here to this initial reaction. The important part here in this initial reaction is to notice how many moles of base are needed to react with how many moles of our unknown acid. This is the important connection here that we need. For every 2 moles of sodium hydroxide base, we have 1 mole of our acid. For every 2 moles of NaOH, we have 1 mole of our unknown diprotic acid. This is the key mole-to-mole ratio we need for this titration problem. So now if we can figure out moles of NaOH or moles of just OH minus, we can go back to then make the connection between moles of base and moles of our unknown acid. We want moles of our unknown acid to then get molar mass of our unknown acid. Remember, for stoichiometry problems, we have to work in moles. What we're told about the base is we have 26.0 mils that were used to reach an equivalence point, and it was 0.700 molar. And to highlight another important point here, because the unknown acid is diprotic, it takes 2 OH minus anions to neutralize each acid molecule, where it takes 2 moles of NaOH to neutralize each 1 mole of acid. That is only because we're working with a diprotic acid. If it were a monoprotic acid, for a monoprotic acid, for example, like HCl and NaOH go on to form water and a salt of Na and Cl. This is already balanced because Na, Cl, 2 H's and 1 O. So this is a monoprotic acid, HCl is. It's monoprotic because it can dissociate into just one of these hydrogen cations. For a monoprotic acid, we then have 1 mole of NaOH for every 1 mole of HCl. Notice importantly for monoprotic acid, 1 mole of base to 1 mole of strong acid. For a diprotic acid, 2 moles of strong base to 1 mole of this diprotic acid. So 2 to 1 and 1 to 1. So it's really important to get comfortable recognizing monoprotic, diprotic, then writing out equations like this. So diprotic acid with base forms water and salt. When this is all balanced, it leads to a 2 moles of base to 1 mole of acid balanced chemical reaction. So this monoprotic, diprotic topic here is also mentioned here in this bullet point. As always, though, let me know if you have any clarifying questions at any point throughout the semester. Now with this mole-to-mole ratio of our base to our acid, we can use the information about the molarity of the base and the volume of the base to then further start to solve this problem. We're told we have a 0.0700 molar solution. Really, I would rewrite this as 0.0700 moles of sodium hydroxide per liter of solution. Then we also do have the volume in milliliters. We were told it took 26 mils to reach an equivalence point. So now we can say 0.0700 moles of NaOH per liter of solution. Then we can get just moles of NaOH by multiplying the volume to 26 mils. We just want moles of NaOH, so then we can connect that to moles of acid. So now to get moles of base, we're still not there for canceling out the volume because this is milliliters, that's liters. So for every 1,000 mils per 1 liter, leading to liters canceling out, mils and mils. This gives us 0.0018200 moles of NaOH. Now with this many moles of NaOH, we can use this mole-to-mole ratio to then get moles of our unknown acid. So it's this many moles of NaOH we just calculated using the molarity and the volume. So remember, concentration equals number of moles over volume. We had the volume, we had the concentration. So to find the number of moles of NaOH, we took the concentration and molarity times the volume. So here, concentration in molarity times the volume. Okay, so we practiced that earlier in chapter 4. So now we got this many moles of NaOH using this reaction, making sure we converted milliliters to liters. Using this really important mole-to-mole ratio, how should we orient this conversion factor to just get moles of H2A or moles of our acid? So we want to cancel out moles of base. So for every 2 moles of NaOH, there is 1 mole of H2A, our unknown acid. This leads to moles of NaOH canceling out. So we're taking this amount divided by 2. Then really importantly, we're left with moles of our acid, which will then help us get our molar mass. So when we take this amount divided by 2, that's 0.009100 moles of H2A. We want the molar mass. So for a molar mass, we need the number of grams per number of moles. At this point, we know how many moles of our acid we have. Do we have the mass of this unknown acid? Let's go back to our setup. Yes, here, right? So we have 0.122 grams of our unknown acid. That's our mass. Now we know the moles of the acid, so we can take the number of grams divided by the number of moles. Molar mass, again, number of grams divided by the number of moles. So there are 0.122 grams of our unknown acid divided by this many moles of our unknown acid. This ratio of a gram amount to a mole amount is going to give us our molar mass. So that comes out to about 134.07 grams per mole of our unknown acid. Considering the total number of sig figs, then our final answer in 3 sig figs is 134 grams per mole of our unknown acid, that's diprotic, or H2A. There are a few similar problems to check out, so 4.11 and 4.12 in your main slide deck. Let's go on to another topic now. Here is still related to titration. So we'll do a little bit more practice on titration, standardizing a base solution using titration. So for this practice problem, we have a need to standardize a fresh solution of sodium hydroxide. We have this many milligrams of acid, a diprotic acid that can be purchased in high purity, and dissolves it in 250 mils of distilled water or deionized water. So just think of this as ultra pure water with no excess or no additional ions. As you can see now, if there are some ions like in tap water that are present, that can interfere with the chemistry of our reaction. So here, distilled water, it's ultra pure water. So here for oxalic acid, H2C2O4, we're told a few things. We're told it's diprotic, so these two protons can dissociate from the molecule. We're told that we weighed out 397 milligrams of the solid acid and then dissolve that into 250 mils of water. That's all just for our acid, so just starting to get organized here. Then our base is sodium hydroxide. We're told that. The student then titrates the oxalic acid solution with sodium hydroxide. So again, in our setup, we do still have a burette of NaOH, but then in the Erlenmeyer flask now, we know all the information about this acid. What we also know then is it took 96.6 mils of sodium hydroxide to reach an equivalence point, given these details, this information about our diprotic acid. Ultimately, we're going to report the concentration in molarity. So we need moles of sodium hydroxide per liter of solution of sodium hydroxide. What is the very first thing we should do given this formula for our acid and this formula for our base? So what we're going to need from these two is, of course, a balanced chemical reaction. So we're going to need a balanced chemical reaction to solve this problem. So some information here as mentioned, we're going to need for the molarity, we're going to need the moles of NaOH in a given amount of volume. We know the volume of a solution that was added to our oxalic acid. So if we have this volume amount, we can just find the moles to then get the molarity concentration for our answer. How do we calculate the number of moles of sodium hydroxide? Well, of course, we need this balanced chemical reaction between our acid and our base. So H2CO4 combines with sodium hydroxide to always form a salt and water, right? So our water here, we can write out H2O. To figure out our salt, we have Na+, definitely as our cation from the base. What about our anion from this acid? So this breaks up into H+ and H+, it's diprotic, and then this must be CO4 with what charge on it if this whole thing is neutral? So 1+ and 1+, this is 2+. That means that the charge here must be CO4 2-. So for the formula for the salts that must form along with water from the addition or the combination of an acid and a strong base, this is going to be Na, using the cross method, Na2 and CO4, just 1, right? So no subscript needed there. So we have this written out, but is it balanced, That is our key question here. Is this balanced? Here we have 2 sodiums and 2 sodiums. Here we have 2 sodiums and 1 sodium, so we need a 2 there. So this is now 2 sodiums and 2 sodiums. For oxygen, we have 2 and 6 total now, so 2 and 4 is 6. Here we have 4 and 1. If we need this side to also have 6 and this has 4, we're not going to adjust this molar coefficient. So we need 2 more here. So how do we make water then lead to this being 2 oxygens? So we needed 2 here. So hydrogen now 4, 2, and 2, that's 4. Sodium 2. Oxygen is also balanced now. How do we also know that we're going to have 2 moles of base for every 1 mole of acid, right? From our balanced chemical reaction, this is a 2. Then out front is this implied 1 for our acid. So this is 2 moles of base for every 1 mole of acid. We also expected this to be the case because we were told we have a diprotic acid. So that can dissociate into 2 protons. So diprotic acid with 2 protons, for every 1 mole of the acid, we're going to need 2 moles of the base to then be balanced. So 2H plus here and just 1 OH minus. So we need double the amount of sodium hydroxide, our base, to then make up for this diprotic acid. So 2 moles of base for every 1 mole of acid. So now we can start to work with this. If we find out the moles of acid, we can connect that to our moles of unknown amount of base. So here we have 397 milligrams into this volume. So with 397 milligrams of our diprotic acid, and if we ultimately want moles of our acid, how do we go from a gram amount to a mole amount? We need to use the molar mass, or grams per mole. To get the molar mass of this diprotic acid, go to the periodic table, 2 hydrogens, 2 carbons, and 4 oxygens. The molar mass then is about 90 grams per mole. To make this work with grams and milligrams, let's also convert milligrams into grams. So for every 1,000 milligrams, there's 1 gram. Let's go ahead and incorporate this molar mass here at the same time. So grams to cancel out, we need to put grams here in the denominator. So this many grams per mole. This is technically 1,000 milligrams and 1 gram. So doing this multiplication and division, is technically a 1 here too. 90.0349 grams per 1 mole. This comes out to 0.0044094 moles. Really importantly, this is still moles of our diprotic acid, right? Notice that it didn't actually matter this volume here. All we needed were this many milligrams to convert into grams, to then convert into moles of acid. Then we can use our mole to mole ratio of acid to base. So for every 2 moles of base, there's 1 mole of acid. In the end, we need the moles of base to get the concentration in molarity. So we're solving for our moles of base here. So we have this many moles of our acid. We need to connect that to the moles of our base. And for every 1 mole of our acid, we know we're going to have 2 moles needed of our base, which is sodium hydroxide. So here we took the milligrams into grams, then into moles of our acid. So moles here of our acid cancels out with moles. Then we can just get moles of our base. So taking this value here times 2 comes out to 0.0088188 moles, importantly now, of sodium hydroxide. We're getting closer to solving for this now because 0.0088188 moles of NaOH and divided into what volume? So we just need this volume here of our sodium hydroxide. So, right, we just want the concentration of this amount in our burette. We have the moles of sodium hydroxide that were needed to neutralize this acid. It took how many milliliters of a solution of sodium hydroxide to do so? It took 96.6 mils of our sodium hydroxide solution. So this gets divided by 96.6 mils. We are definitely not yet in molarity though, because this is now moles per milliliter. To get this into moles per liter, there are 1,000 milliliters per liter. Mils and mils cancels out. Now we can get a moles per liter. This comes out to 0.091292 moles per liter. Same units as molarity now. To report this in just 3 sig figs, here's our first sig fig, 1, 2, 3. This 9 bumps this 2 up to a 3, so 0.0913 molar of NaOH. So then here is indeed our final answer of sodium hydroxide in the correct units of molarity. So we talked about titrations now with acids and bases. I've also been mentioning that we can have titrations with redox style reactions. I also want to point out that these practice problems have again been with our diprotic acids. So we did a lot of practice with diprotic acids. We can also, of course, have monoprotic, so monoprotic and triprotic acids. So we would go through the same steps for monoprotic and triprotic. Just keep in mind that the 2 moles of base per 1 mole of acid was for a diprotic acid. Okay, so let's keep that in mind, and now let's go back to talking a little bit more about these redox titrations. So let's do an example problem with a redox titration, just to show you the math and the setup for this. So we have 16.42 milliliters of 0.1327 potassium permanganate solution. So that's here in our burette. That's needed to oxidize 25 mils of iron 2 sulfate. Why is this iron 2 and not iron 3? So we have FeSO4 2-. For using the cross method then, 2 would be down here. SO4, it gets simplified to just FeSO4. So this had to have been a 2 as well for these to get simplified, meaning this charge on iron had to be 2+ and not 3+. So this is definitely iron 2, so Roman numeral 2, sulfate. Then what is the concentration of iron 2 sulfate in units of molarity? For the dissociation of potassium permanganate, it's going to break down into potassium ions and permanganate ions. For iron and sulfate, again, iron 2+, we figured out, and sulfate 2-. For this combination, so redox reaction of our 2 initial reactants, the net ionic equation ends up coming out to this. So when all electrons have been transferred, everything's been oxidized and reduced that can be, this turns out to be our net ionic equation. We'll get into balancing redox reactions in Gen Chem 2. So just as a heads up, this is our balanced redox reaction, but we won't be balancing redox reactions in this semester. This is the same slide I showed you earlier. So here we wrote out this dissociation, but also we could have, if it was a 3, this would be a 3 molar coefficient from this 3 subscript. So we could just write out 1 to 1 to 1 molar coefficients because these subscripts are all just 1. Right, so permanganate ions, MnO4- K+, subscript of 1 and 1 to form potassium permanganate. 2+ and 2- for iron and sulfate gets simplified to 1 and 1. So that's another 1 to 1 molar coefficient or mole to mole ratio here. This has a 3 to 1 molar ratio because this subscript has to be 3. This one has to be 3 because potassium is an alkali metal, forms +1 cations. Phosphate is PO4 3-. So then with the cross method, 3 comes down here, 1 comes down here. So this 1 is implied. We don't include that. This comes out to K3PO4. So hence the 3 here and the 1 here. Now to solve for the molarity of iron 2 sulfate, we need the molarity in units of moles of iron 2 sulfate per liter of solution. We do have the total volume of the solution that was given. So to solve for this, we need the moles of iron 2 sulfate. To find moles of iron 2 sulfate, we can look at this balanced net reaction. Again, you don't need to worry about balancing redox reactions in this semester. So here is the balanced reaction for this redox reaction. So to connect iron sulfate and permanganate, we have a 5 moles of iron 2 plus for every 1 mole of permanganate. Then how many moles of potassium permanganate are contained in 16.42 mils of this molar concentration of potassium permanganate? Because that was given in the initial problem. So here these values were given in this initial problem. So with a molarity of 0.1327, we can go ahead and write this out as moles of potassium permanganate per liter of solution. Now to incorporate the volume here, let's convert liters of solution into milliliters or vice versa, either way. Let's actually keep this in liters. So we'll say 16.42 milliliters of solution. These are not yet canceled out. So let's convert 1,000 milliliters per 1 liter, leading to liters of solution canceling out, mils canceling out. Here we'll just have moles of potassium permanganate. That comes out to 2.179 times 10 to the negative third moles of potassium permanganate. Now using this balanced net reaction, we can connect potassium permanganate to iron 2 plus. Remember here, so for every 1 mole of potassium permanganate, there's 1 mole of permanganate. So here for every 1 mole of potassium permanganate, there's 1 mole of MnO4 minus or permanganate. So then really this is the same thing as this many moles of just MnO4 minus, right? Because it's a 1-to-1 mole ratio. For every 1 mole of potassium permanganate, there's 1 mole of permanganate. So here we have this many moles of potassium permanganate. I'm going to show you all of this in one reaction here. For every 1 mole of potassium permanganate, there's 1 mole of permanganate. At this point, we would cancel out moles of potassium permanganate and moles of potassium permanganate. Now to connect permanganate to iron 2 plus. For every 1 mole of permanganate, there are 5 moles of iron 2 plus. So 1 mole of permanganate, for every 5 moles of iron 2 plus, we put moles of permanganate in the denominator. Now this cancels out. So far in units, we're left with moles of iron 2 plus. Then to connect iron 2 plus to iron 2 sulfate, it's also a 1-to-1 mole ratio. For every 1 mole of iron 2 plus, there is 1 mole of iron 2 sulfate. So moles of iron 2 plus cancels out with moles of iron 2 plus, leaving just moles of iron 2 sulfate now. Doing all of this division and multiplication, it's actually just multiplication because we'd be dividing just by 1. That comes out to this many moles of iron 2 sulfate. So 1.090 times 10 to the negative 2 moles. Then to finish this out, we do have 25 mils of that solution. So now we can divide the moles of iron 2 sulfate by the total volume to then get our molarity. So we're going to take this many moles of iron 2 sulfate divided by the total volume, of course converting this into liters. So for every 1,000 mils, there's 1 liter. So mils and mils cancels out, leaving just moles per liter. And so really importantly, moles of iron 2 sulfate per liter of solution is then our molarity. So to solve these redox style reactions, this is our final answer here, as long as it has the correct number of sig figs. All these values here have 4 sig figs, so this is our final answer here. Our final answer here in 4 sig figs. To solve a redox style problem, you're going to have to know this balanced chemical reaction. So this would have to be given to you, this net ionic reaction or equation for redox reactions. Then it's going to be really important that you feel comfortable taking an ionic compound and writing out a balanced chemical equation for the dissociation into its respective ions. You should be able to do this for a 1:1:1 mole ratio, 1:2. So all these different ionic compounds, can practice breaking them down into their respective ions. And then really importantly, those reactions have to be balanced. So balanced chemical reactions and moles, we've seen the importance of both of those. We're at the end of chapter 4b and therefore at the end of chapter 4 now. As always, if you have any questions about anything, definitely let me know. So I'll talk to you next time for chapter 5, and I hope you're all doing really well. So I'll talk to you soon.